morning, good afternoon, everyone. Welcome. Thank you for joining us today in our webinar. My name is Ismail Benayoun, and I am the US West Technical Director at Altair. Today is the third session already of our webinar series on how to accelerate your electronics device designs. So this webinar series is actually composed of two major tracks. The first one, mechanical series, which actually covers the broad scope of product design, from concept evaluation to manufacturing, going through some of the most complex simulation techniques and use cases. We will be demonstrating how Altair Multiphysics platform offers the most comprehensive simulation and optimization solution in the market. The second series, today's actually, is focusing on electromagnetics. Our high-frequency electromagnetic experts will be covering topics of PCB design and verification up to manufacturing, antenna design, process, their placement, performance evaluation and optimization, and also they will show how to solve coexistence and interference issues between connected products. All of this using Altair's EDA and EM simulation platform. Both series will cover examples and models from various types. In fact, we will demonstrate the different solutions using various electronic devices such as smart speakers, hand controllers, or Bluetooth mouse. We will cover the various needs in the product development cycles, from concept to reality, with the analysis of components, sub-assemblies, systems and systems of systems. In few words, we want to share and we will share with you how Altair helps companies to reduce time to market by enabling advanced simulation and optimization and machine learning, all leveraging one simulation platform. So today's webinar is about lead time reduction for PCB design and verification. We will walk you through advanced and automated workflow where PCB verification by design for electrical will be detailed, as well as PCB solver capabilities, such as signal integrity and thermal analysis will be demonstrated. Altair's strength resides in the combination of the advanced capability of its software and the engineers involved at our customer sites solving real-life problems. One example I wanted to share with you, and that you can see here, is actually Samsung SDI in South Korea. Jae-Woon Lee, chief researcher, have explained in a very long video how Altair POLIX have been adopted and integrated in the product development cycle for their PCBs. This has enabled them to significantly reduce their lead time and consequently save cost. So maybe some of you have heard about Altair before, and if not, please allow me to take 2 minutes to tell you a little bit about us. Our vision guides our actions. We do our best to develop the cutting-edge technology that can transform customer decision-making with simulation, data analytics, and high-performance computing. With more than 11,000 customers around the globe, my 3,000 colleagues and I are located all over the world, developing and supporting more than 150 advanced software products. These softwares are the fundamentals of our broad solution portfolio, the one that we are offering you. From design and model visualization to multiphysics solvers to data analytics and high-performance cloud computing. While our roots are in the automotive industry when founded 35 years ago, we today develop solutions that are designed to deliver excellence across various industries. And on this slide, you can see some of our customers in the various verticals and industries. So back to today's session, I would like to introduce the presenters and people who worked on this. Aniket Hedge, project engineer and with a domain of expertise and experience focused on design and verification of printed circuit boards, embedded software development, and math tools. Today's materials have been prepared by Aniket and Jae-Hoon Kim. He is electromagnetic application engineer with Altair for more than 20 years, with more than 20 years of experience in high-frequency electromagnetic, antenna design, RF microwave, and EM simulator, as well as PCB design and verification. Without further ado, Aniket, the floor is yours.
Thank you, Ismail, for the introduction. Hello all, I am Aniket Hegde. I work as a project engineer at Altair, and today I will take you through this webinar named Reduced PCB Design Reviews from Design to Manufacturing using Altair EDA Solution. This event will take place in 2 sessions. In session 1, we will discuss the evolution of consumer electronics and consider one application of consumer electronics as an example. Using this example, we will dig deep into some of the design considerations to showcase the simplicity of our solution. And session 2, where we will address these considerations via design verification toolset and design solvers, which will be a part of a unified Altair solution. Well, let's get into session 1. We have seen evolution of electronic devices in all forms and sizes, from CRTs to smart TVs, from ENIAC machines to tablet computers, from Dynatec, which is the first cellular phone, to smartphones are only drops in the ocean when it comes to the advancements in the field of electronic devices. This evolution has impacted the use of electronics in household appliances as well. We can safely say that electronics have well and truly found their places in everyone's home. We find these products in a variety of applications ranging from entertainment to security as well as convenience. For this webinar, we will investigate one of the complex consumer devices which are amongst the first ones to arrive at our homes and are nowadays embedded in various other electronic appliances as well, speakers. We will understand the basics of speakers and then go through the process of a complete design cycle for a wireless speaker. Evolution of speakers. Evolution of speakers demonstrate another example of advancement in the field of electronic devices. From only having the option of large speakers with tangled wires, we now have the option of wired speaker with minimal wiring, along with wireless speakers and smart speakers. Well, let's have a look at the product development cycle of a wireless speaker. However, it should be noted that this development cycle is valid for most of the consumer electronic products. Well, we start with the concept design, evaluating the features we want to embed inside the structure we decide to develop. Then comes the virtual validation, basically validating the integrity of the system and checking group performance such as thermal behavior. Lastly comes the verification, wherein each component of the system is verified and put to test under critical conditions, and barring any last-minute changes, we send it out to production. Looking at virtual validation or virtual prototyping in detail, virtual prototyping has been an integral part of product design ever since the inception of simulation-driven design. This technique has saved fortunes with product design companies in terms of time and resources. Once the idea is generated, we simulate all the components needed for the product. In our example of wireless speaker, it would be the speakers, the enclosures, the wiring, and the PCB, of course. The idea of virtual prototyping is putting these components to go through rigorous test cycles via software simulation, which encompasses the basic necessities such as electromagnetics, thermal, vibration, drop. To go into subcategories, we have membrane characterization, PCB design verification and analysis, antenna design and integration, and coverage and interference. For this webinar though, since there are so many topics, for this webinar, we will be covering PCB design, verification, and analysis in detail. Looking at the first step, let's look at the typical workflow of any PCB design. Like every other design process, PCB design starts with an idea and choosing the right components for the idea. This is followed by creating schematic and generating netlist and also laying out the PCB. This is basically the end of the first design cycle. However, this design goes through a review process by generating output files such as Gerber files and drill files, and any changes needed would then be fed back to the design team. Once the review is successfully completed, a bill of materials is generated, and then the design is sent out for manufacturing. Having looked at the workflow of a typical PCB design, let's look at some design considerations for some designs for wireless speakers. The most important part of a wireless speaker is the PCB, as it hosts all the functional modules. And looking closer into the design of a PCB for a wireless speaker, the main sections involved are the wireless section, the audio section, power supply, and charging. As we can see in these examples, these sections are combined into a PCB which are produced in various sizes and shapes. Looking at these design patterns, we have come up with an Altair solution for a wireless speaker. As you can see on the right, the speaker has various essential components like the acoustic port, heat exchanger, fan, and of course, the printed circuit board. On the left, you can see a closer view of the printed circuit board. And let's learn about the trends, design considerations, and challenges in a PCB design cycle. Looking at the market trends, cost reduction, reducing cost price is an underlying factor when it comes to any electronic product. This is following the general notion that reduced cost would attract a larger group of audience. Compact size, miniaturization, it continues to be a trend for most of the consumer electronic products for decades now. However, certain products are going against this practice. For example, cell phones are now increasing in size to include a rich variety of features as they become a source for media and entertainment, and not only for basic needs like calls and receiving texts. Uninterrupted connectivity. Since most of today's products rely on wireless connectivity and connected to internet, a need for uninterrupted connectivity has become a prime necessity. Time to market. Time to market is important in the realm of an ever-changing market to avoid being late, which would erode the addressable market that you have to sell your product into. Seamless audio streaming. This is also something which is specific to audio devices, wherein the connectivity with the audio source shall be seamless to provide seamless streaming at the output. Clear audio quality. This is also something which is very specific to speakers and devices with audio output. A clear audio quality output is always desired to avoid any loss of information. Well, here is a block diagram considering some of the essential components of a wireless speaker. For connectivity, we have the Bluetooth IC, we have the charging IC for battery charging and power management, LCD driver to operate the LCD and display important details on the screen, the audio amplifier, of course, which holds the responsibility for converting the electrical streams into an audio output, and the controller IC, which governs the synchronization and proper functioning of all the components previously mentioned. And here we have an in-house PCB design which constitutes of all the components previously mentioned in the block diagram. We have the Bluetooth IC and the antenna. We have the LCD driver. Here is the charging IC. Here's the controller IC. We have the memory IC for storing the pairing information and battery information as an example. We have audio amplifier, again, one of the main constituents. And here we have the speaker output where you can straight away connect 2 leads into or 4 leads into the speaker and to get a good quality output. Well, looking at the design, now look at some design considerations. So basically when it comes to designing the PCB and proper functioning of a speaker. Noise-free differential audio lines and shielded audio lines and thermal behavior of the main ICs are essential in attaining proper audio quality. Basically, and satisfaction of specific impedance and safe use of high-speed bus lines, which are critical for high-speed performance, are some of the basic design considerations when it comes to a speaker design. Throughout this webinar, we will look at ways to make sure these design considerations are addressed and are implemented correctly. To make sure the audio quality is not affected, we will make use of the DFE tool for the audio lines and thermal analysis to determine the thermal behavior of the main ICs. And to ensure the high-speed performance is up to standards, we will make use of the signal integrity analysis tool to confirm the specific impedances are satisfied and high-speed bus lines are traced properly. And let's look at an Altair solution. Altair offers a unified, fast, and accurate solution addressing all the design considerations. The PCB design can be imported into a PCB modeler where we can perform signal integrity, power integrity, along with thermal analysis and various PCB verification methodologies like DFE, DFM, and DFA. Our solution is a simulation-driven process that reduces physical testing. Improves decision making and saves time. As you see ahead with our solution, it would save time and resources as it is completely simulation-driven and no physical testing is involved. And the reason we have called it as a unified solution is because all those verification and analysis performed to address these considerations are all coming under one umbrella of a software suite, Altair POLEX. Altair POLEX is a PCB level EDA software suite covering design review, analysis, and manufacturing to significantly reduce development cycles, which is while providing a common application for schematic engineers, PCB designers, CAE analysts, and manufacturing engineers to communicate. The main features of Altair POLEX involving the PCB modeler, which is a strong tool to import design from a host of designer tools and work on it. The unified part editor, which is a one-stop shop for viewing and editing electrical, thermal, and geometrical properties of all the parts in the PCB. The solvers and verification tool, basically, which is used to perform various checks on the PCB. And last, but surely not the least, the logic and CAM to view the logic of the circuitry via schematic or CAM view. The PCB solvers, which involve the signal integrity and thermal analysis, and the PCB verification tools, which include the DFE check, can all be found inside one PCB modeler window itself. Having looked at that, we'll go ahead with the second session, where we will see in detail how the design considerations are addressed using Altair POLEX. Well, before diving into the solution, let's have a recap on the considerations that we saw a few slides before. And on the left, we'll have the design considerations, and on the right, we'll have the solutions. So these are the design considerations we addressed. And on the right, looking at the solutions, we have DFE for verifying the considerations regarding audio lines. We have signal integrity for high-speed bus analysis, and we have thermal analysis to review the thermal behavior of the main ICs. Basically, all the design, verification, and signal integrity analysis we have decided are performed on three main nets: the memory lines, the USB lines, and audio lines. Having looked at those nets, let's have a look at our first verification methodology, the DFE. Before getting into the procedures for DFE, let's answer a couple of basic questions about DFE. Let's start with, why do we have to do DFE? DFE has become an important aspect in today's date with high-speed designs and increased complexity. DFE check has also become important following the trend for small quantity production and short products life cycle. Along the same line, due to rapid changes in technology, DFE check helps save time and resources. Let's answer the second question. When do we do DFE? DFE check is usually carried out as the first post-routing step and before getting into solvers like signal integrity and thermal analysis. Importance of DFE. As DFE is done via simulation and not on actual hardware, it would obviously save cost and delivery time. But for that reason, it is not a matter of choice, but a necessity for all electronic companies. Understanding the DFE workflow is crucial, and with Altair POLEX, it couldn't have been more straightforward. Well, you start by obtaining the design files and import them to POLEX PCB. The POLEX PCB modeler has an easy integration with a host of designer tools. Secondly, we consider the company design rules and the ODM client rules. These rules are integrated as DFE rules. Applying these rules to the design, we get the DFE results, which is then sent to the engineer to evaluate and modify the design, or sent to the manufacturer if no modifications are needed. Well, having a look at the workflow, let's get into the first DFE check by looking at the first design consideration. Differential audio lines, basically impacting audio quality. In order to ensure decent audio quality, we need to have audio paths on the PCB free from any sort of noise. Well, if we consider a regular audio line, basically a signal line and ground, and if noise seeps into either of the lines, then we will have a noisy output line, which would lead to an undesirable audio output. On the other hand, if we have a differential line for audio, if noise enters into any of the signals, it will enter both the traces due to the vicinity from each other and the coupling between them. Since these two lines are differential lines, the noise on both lines would cancel each other out, and the net noise on the output would essentially be zero. Hence, we have used differential lines for audio since they have stronger immunity against noise. The strength of a DFE pair, a differential pair, is defined by its line separation and coupling ratio. In this case, let's try to verify these two parameters with our desired values of line separation of 0.754 millimeters and the coupling ratio of 80% by using the DFE check tool. Here is a graphical representation of explaining the same. Now we'll see the results and how the results look like. We have got two failures. The first fail is due to the coupling ratio being slightly lesser than what we desired. The second fail is due to the separation between greater than basically greater than a predefined range. This result should be sent back to the designer for evaluation and modification. Well, now having looked at our first design consideration, let's move on to the second one. Another added layer of protection for audio signals against noise is shielding them with ground planes. And this is how this is a graphical representation of shielding the audio lines via ground planes. Let's try to verify the shielding of the differential lines using again the DFE tool. We have and as we have set a minimum shield ratio for both horizontal and vertical plane to be 80%. And here is a graphical representation of basically the shielding. And here we'll see the results, how they look like. The results suggest there are no failures, and we will see that 14 cases were passed without any failures. This means the audio lines are properly shielded with ground planes to avoid any noise seeping in. Before we go ahead, I want to pause for a moment and would like to address a few questions and answer them with the best knowledge I have.
Thank you, Aniket. I think this is a really good timing. We've had some questions already coming in. few of them are on the logistics side. So many people asked if this presentation can be shared. I just want to remind everyone that this session will be recorded and available on our website, and we can work with you personally to get the version of these slides and more informations, of course. Now I have a few technical questions for you, Aniket, here from some of the audience. So the first one is it possible to customize the DFE rules for our specific design requirements?
That's a good question. Yes, once you define the rules, you can save the rules into an ASCII file, basically like creating a template. And then you can re-import that and basically load those rules, and you can you can customize the rules and run the DFE again.
Okay. Second question here, can we link the failed items to the original ECAD in order to help the designer identify where is the failure and modify the design?
Another good question, actually. And yes, of course, it is possible as well. You can link the failed items to the original ECAD, including the location and object link for almost all the ECAD interfaces we support.
Okay. Apart from the differential nets you have shown, what other items does Altair's DFE cover?
That's an interesting question. So Altair DFE, of course, it covers a lot of aspects. For example, along with differential net, it can also cover DFE for electrical, including high speed, power, I can say component separation, net separation, EMI ring stability, and many more. Yeah.
Okay. One last question here, I think, is does Altair DFE support batch processing?
Yes, it does. In fact, it has various API functionalities for PDM and PLM links as well. So PDM basically means product data management, and PLM basically means product lifecycle management.
Okay, thank you, Aniket. I invite the audience to keep asking questions. We will have another session for the Q&A later. I want to make sure that we go through some of the rest of the material here. The floor is yours again, Aniket.
Thank you so much, Ismail. Now we will go through the next session, basically covering the signal integrity. So going ahead to look at our next design consideration, let's understand signal integrity analysis in short. As we did for DFE, let's answer a few basic questions. Well, starting with why. For short traces with low bit rates, a simple conductor can transmit signal with sufficient fidelity. However, this problem arises at high bit rates and for long traces, where various factors contribute to degrading the electrical signal. And if the degrade is beyond a certain point, it could lead to errors in information parsing, which would eventually lead to failure of the system. This is where signal integrity analysis comes in to analyze and mitigate these impairments before manufacturing. Well, this takes us to the second question. When do we do DFE? When do we do signal integrity? Well, signal integrity, along with other solvers, is conducted after routing and success with DRC checks and before manufacturing the board. So as you can see, this is where we do the signal integrity along with other solvers. Well, looking at the signal integrity analysis provided by Altair POLEX, here are some of its features or advantages. So the main uniqueness of this tool is it is a unified solution. What that means is you can perform verification, signal integrity, and thermal analysis all inside the same modular. The signal integrity tool covers a large variety of solutions. For example, network analysis and multiple memory line analysis, which we'll see ahead, along with transmission line analysis and crosstalk analysis, just to name a few. And it is an extremely fast solution as minor alterations and what-if study are easily implemented under this toolset without breaking a sweat. Another reason why it's fast is due to the usage of combination of 2.5D solvers based on integral equation solver using boundary element method along with method of moment for trace modeling, and 3D EM field solvers basically used for FEM for pad, basically using FEM for via or pad modeling. So having looked at the importance of signal integrity, now let's look at the workflow of signal integrity, which is like DFE, crucial to understand. And like I said, like in DFE, we import design files from other design tools to POLEX PCB. And in this case, we obtain or create the IO buffer models for all the essential components. IO buffer model files could be SPICE model files or IBIS models or linear models, and even S, Y, and Z parameters. Well, after inputting the model files into the system, the POLEX signal integrity tool uses the Polyworks SPICE engine, an inbuilt engine, which would run the signal integrity analysis and extract results such as parasitic values, network models, waveform for signals, and even generate table-driven result. Basically giving out waveforms, S parameters, I diagrams, and even net topology. Now, having looked at the workflow, let's look at the design considerations and how signal integrity analysis takes care of these considerations. So the third design consideration is regarding high-speed performances. So for seamless connectivity, we have to make sure the data lines of USB meet the requirement of the USB standard, one of which is they should match the impedance requirement for the entire operating frequency range. If these requirements are not met, there could be errors leading to information loss, which may result in improper functioning of the system. Well, having seen that, let's try to verify the performance of the USB data lines via network analysis under signal integrity analysis. Basically, looking at the conditions, we have chosen the transmitter port to be the microcontroller unit and the receiver as the USB connector. Also, we will be checking the signal over USB 2.0 specified range of 480 megabits per second, which basically comes down to a pulse width of around 1 nanosecond. Here is the graphical representation of the USB line connected to the controller IC. Now, before we attain the results of the network analysis, let's look at another important feature of signal integrity network analysis tool, the network topology analyzer. This basically helps in reviewing the net structures between two components. Also, it helps in getting a what-if study via creating and modifying topology and checking the results of each modification. Well, having looked at the network topology, let's go back and view the results of the network analysis without modifying the topologies. So we'll be looking at the results via the waveform viewer window. Let's first look at the transmitted waveforms, which are basically square waves operating at low voltage, transmitting from the microcontroller to the USB connector. Now, looking at the result on the connector side, we see the waveforms are attenuated heavily and no longer represent a square wave, which we had at the input. The main reason for the attenuation is the inconsistency of the impedance between the differential lines, which result in failure in matching the impedance requirement for the USB standard. These results can be sent out to the designer for review and to perform necessary modification in the design. Now, let me demonstrate what I exactly meant by what-if study. So as you can see, the length, basically the topology, can be modified. Now we've changed it from 83 to 10, and we can easily run the network analysis. And here we see the results where you can see the output waveforms and the corresponding input waveforms. Again, for the negative and the positive lines, we can see both. And as we see in the video, it is very easy to adjust basically the network topology. And now here we'll see how how the modified topology has a closer representation to the input square wave than that of the original topology. Well, there is a ripple effect after each transition though, which can be taken care of by adding filtering capacitors. In this way, we saw how easy it is to modify the topology to see what effect would it have on the waveforms. Various modifications can be done to the topology within a snap of a finger, and then the topology which outputs the desired result can be captured. Having seen that, let's look at our fourth design consideration, which is again involves high-speed performance, wherein the high-speed bus lines of memory needs to satisfy the DDR regulation. Here we can see we have decided on a few network analysis conditions. We have the transmission port as microcontroller and reception port as memory. We have a data rate of 256 megabits per second. We have clock rate running at 133 megahertz, and we have also set the input high and input low voltage. But once these conditions are set, we will see the results on the next slide. And looking at the result, we see the clock signal is in pink, and the rest are the address signals. It has to be noted that all the signals are viewed on the receiver side, and due to stray capacitance along the trace, we see voltage margin amongst the signals. However, it has to be noted that for the decided frequency, we observe the timing delay between the clock line and the address line seem to be very minimal, and the signals appear to be synchronized. The main reason for this is we are operating at USB 2.0 standard, which does not demand very high frequency. Similar to this, much more detail can be analyzed using the I block or the red square, which you see on the screen. Having looked at the signal integrity feature, let's look at another key feature, which is thermal analysis, which is also covered under Altair POLEX. Before we get into thermal analysis solver of Altair POLEX, let's look at benefits of performing thermal analysis on a PCB. So mainly by performing thermal analysis, we could detect and correct potential thermal problems like excessive component junction temperature and uneven board temperatures. And by performing these analyses beforehand, we could prevent the high cost and time involved in over-design. By observing the thermal behavior of the PCB, we could provide thermal requirements for the entire system. For example, if we need an additional fan to cool down the PCB if it's inside an enclosure. Adding to that, we could accumulate knowledge for better thermal design. Thermal analyzer essentially analyzes components board temperature and component junction and board temperatures with FEM models. This is done so using thermal engines, which comprises of thermal diffusion equations and heat transfer models, namely conduction, convection, and radiation. Two of the most common compact thermal models for IC packages are the two-resistor model and the Delphi model. And you can see on the bottom right, the two-resistor model is shown in the graphical view. Having looked at the benefits of thermal analysis, let's look at an example of the wireless speaker via thermal analysis in Altair POLEX. It is understandable that the main sources of heat on this PCB would be the charging IC and the audio amplifier. If not carefully observed, this heat could result in degradation of audio quality. Not to forget, the health safety would be under the radar as well. The key constraints for deciding thermal analysis is shown here. We have chosen gravity direction to be the negative y-axis. We have chosen ambient temperature as 25 degrees, and we have chosen that the power level to be operating at 80%, and board glue material as air, meaning no glue is actually attached on the board. Also, for our analysis, we have chosen natural air convection, meaning there is no forced air. Here is the graphical representation of the constraints, and here we see how the values are fed into the thermal analyzer. After feeding the inputs and running the analyzer, we can now see the output. Here we see that the bottom left part of the board has higher temperature as compared to other parts of the board. This is due to the presence of power conditioning and battery charging circuitry in that area. Not to forget, there is also the audio amplifier, which is located slightly lower to the battery charging area. Well, what effect will it have if we introduced forced convection, for example, an electric fan inside the enclosure? And now we'll see how we can change the convection type and rerun the analysis with ease. The actual surface temperature is shown on the bottom left, where my cursor is. Now we introduce the forced air convection with speed of 5 meters per second. And now, after doing this, we adjust the scale and basically we run the analysis and then adjust the scale. And there you go. Now we'll just readjust the scale to match the previous result. And here we can see when we introduce forced air convection of 5 meters per second airflow, we clearly see the entire board is relatively cooler. And the maximum temperature has come down from 85 degrees when it was in the previous without any air convection to 55 degrees max. Well, to summarize what we learned from today's sessions, the trends and challenges in electronic industries were discussed via the example of a wireless speaker. Using the same example, the design considerations of any PCB involving complex functionalities were discussed. And lastly, by addressing these design considerations, we observed how Altair POLEX is a truly fast and unified solution. Basically address all the challenges, and there are many more challenges when it comes to designing a PCB. We have addressed a few problems which are somewhat very specific to wireless speaker, but we also have the capabilities to address designs for any PCB from any industry. And Altair POLEX also supports these features and addressing the capabilities of various industries.